Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast emptiness of space, resources become the ultimate currency. As humanity stretches beyond the confines of Earth, our ability to gather and utilize resources in space will determine how far we can go. At the center of this cosmic resource, revolution sits our closest celestial neighbor, the Moon, poised to become the solar system's first extraterrestrial gas station. The concept sounds like science fiction, mining the Moon's surface for water, splitting it into hydrogen and oxygen, and using these elements as rocket propellant. Yet NASA's plans to establish a lunar fuel depot represent one of the most pragmatic approaches to sustainable space exploration in the 21st century. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The fundamental challenge of space travel has always been the tyranny of the rocket equation, first formulated by Russian scientist Konstantin Tsiolkovsky in 1903. This mathematical relationship reveals the brutal reality. The farther we want to travel, the more fuel we need. The more fuel we carry, the heavier our spacecraft becomes. The heavier our spacecraft, the more fuel required to move it. This creates a vicious cycle that makes deep space exploration prohibitively expensive when all resources must be carried from Earth. Breaking this cycle requires a paradigm shift. Instead of bringing everything from Earth, we must learn to live off the land, a concept known as in-situ resource utilization, or ISRU. The Moon offers the perfect testing ground for this revolutionary approach, sitting just 3 days' journey from Earth. The game changer came in 2009 when NASA's Lunar Reconnaissance Orbiter and the Lunar Crater Observation and Sensing Satellite LCROSS confirmed significant quantities of water ice in permanently shadowed craters at the lunar poles. These regions, never touched by sunlight, serve as cosmic freezers where water has accumulated over billions of years from comet impacts and solar wind interactions with the lunar regolith. Later missions strengthened these findings. India's Chandrayaan-1 detected water molecules across the lunar surface. In 2018, scientists analyzing data from India's Moon Mineralogy Mapper confirmed ice deposits in the polar regions. More recently, in 2023, Japan's SLIM mission and China's Chang'e missions added to our understanding of lunar water distribution. The presence of lunar water transforms the economics of space exploration. Water ice can be harvested and processed into liquid hydrogen and liquid oxygen, the same propellant combination that powered the main engines of NASA's space shuttle. By establishing fuel production facilities on the Moon, spacecraft could depart Earth with minimal fuel, refuel in lunar orbit, and continue to Mars or beyond. NASA's Artemis program, named after Apollo's twin sister in Greek mythology, seeks to return humans to the Moon by 2025. Beyond the historic significance of putting the first woman and person of color on the lunar surface, Artemis has a more practical goal: establishing a sustainable human presence and proving the technologies needed for ISRU. The initiative includes plans for the Lunar Gateway, a small space station orbiting the Moon that will serve as a solar-powered communication hub, science laboratory, and holding area for rovers and other robots. More importantly, it will function as a pit, stop where spacecraft can dock and refuel before venturing deeper into space. The Moon's potential as a cosmic filling station hinges on a deceptively simple process: electrolysis. This chemical reaction, familiar to high school science students, uses electrical current to split water molecules, H2O, into their constituent elements, hydrogen and oxygen. On the Moon, solar arrays would generate the electricity needed to power this process, creating a sustainable, carbon-free fuel production system. The journey from lunar ice to rocket fuel begins with extraction. Unlike Earth's easily accessible water sources, lunar water exists primarily in two challenging forms: as ice crystals embedded within the regolith in permanently shadowed regions, and as hydroxyl compounds, OH, chemically bound to lunar minerals, across the surface. Accessing the water ice in permanently shadowed craters presents significant engineering challenges. These areas exist in a perpetual deep freeze, with temperatures hovering around -230 degrees Celsius, cold, enough to preserve water ice for billions of years, but harsh enough to freeze and crack ordinary equipment. Any harvesting technology must operate in these extreme conditions, while navigating terrain never directly observed by human eyes. NASA and private companies are developing specialized rovers equipped with heating elements to extract ice through sublimation, the direct transition from solid to gas. Once vaporized, the water vapor can be captured, condensed, and stored. Alternative approaches include mechanical mining using drills or scoops to collect ice-bearing regolith for processing. The Viper, Volatiles Investigating Polar Exploration Rover, mission, scheduled to launch in 2026, will be the first targeted investigation of the Moon's polar resources. This golf cart-sized rover will carry instruments capable of analyzing the composition of lunar soil and ice, helping scientists map potential harvesting sites. Once collected, the water undergoes purification to remove lunar dust and other contaminants. The purified water then enters electrolysis chambers, where specially designed catalysts improve efficiency. Current Earth-based systems achieve approximately 80% efficiency, but engineers are developing space-hardened systems that can maintain optimal performance despite radiation exposure and temperature fluctuations. The resulting hydrogen and oxygen must be liquefied for storage. No small feat considering liquid hydrogen must be maintained at -253 degrees Celsius. Cryogenic storage technologies are being developed with multi-layer insulation and passive cooling systems that can maintain these temperatures with minimal energy input. The chemistry extends beyond water processing. The lunar regolith contains approximately 42% oxygen by weight, bound in silicate minerals. NASA's MOXIE experiment on Mars has already demonstrated that oxygen can be extracted from carbon dioxide in the Martian atmosphere. Similar technologies could extract oxygen directly from lunar soil, supplementing the water-derived supplies. Additionally, helium-3, deposited on the lunar surface by solar winds over billions of years, represents another potential energy resource. Though currently impractical for propulsion, helium-3 could theoretically fuel future fusion reactions, providing power for lunar bases and fuel production facilities. The integration of these chemical processes creates a resource pipeline, from extraction to processing to storage, that could produce approximately 16 metric tons of propellant annually from a single modest processing facility. While this may seem minimal compared to the thousands of tons consumed by modern rockets, in the vacuum of space, where every kilogram counts, this represents a revolutionary capability. Private companies like Lunar Resources and Transastra are developing specialized equipment for these operations. Their designs incorporate redundant systems, radiation hardening, and dust mitigation technologies essential for long-term lunar operations. The hardware must be lightweight enough to transport from Earth, yet robust enough to operate for years with minimal maintenance in the lunar environment. Establishing mining operations on the Moon presents unprecedented engineering challenges that push the boundaries of human innovation. The lunar environment combines extreme temperature swings, radiation exposure, vacuum conditions, and 1/6 Earth's gravity, creating a hostile workplace for both machines and humans. The lunar day-night cycle stretches across 29 Earth days, with surface temperatures ranging from 120 degrees Celsius during the day to -150 degrees Celsius at night. Any equipment must withstand these thermal extremes while maintaining operational integrity. Metals expand and contract, lubricants freeze or evaporate, and electronic components fail under such conditions. To address these challenges, engineers are developing thermal management systems that incorporate radiators, heat pipes, and multi-layer insulation. Some designs feature thermal waddies, artificial heat reservoirs that store solar energy during daylight and release it slowly during the long lunar night. These systems must operate without traditional cooling fluids, which would boil away in the vacuum. The lunar dust, or regolith, represents perhaps the most insidious engineering obstacle. Unlike Earth soil, lunar dust has never been weathered by wind or water. The particles remain sharp and abrasive, capable of wearing down mechanical joints, clogging filters, and degrading seals. During the Apollo missions, dust damaged equipment and caused health concerns for astronauts. Modern designs incorporate magnetic fields to repel the electrically charged dust particles and specialized coatings that resist dust adhesion. Sealed compartments with positive air pressure protect sensitive components, while electrostatic precipitators remove dust from extracted materials before processing. The vacuum environment presents another layer of complexity. Without atmospheric pressure, metal surfaces can cold weld together on contact. Traditional lubricants evaporate instantly. Heat dissipation becomes challenging without convection. Engineers are developing solid lubricants, magnetic bearings, and specialized alloys that can function reliably in vacuum conditions. Power generation presents another critical challenge. Solar arrays must withstand micrometeoroid impacts and dust accumulation, while generating sufficient electricity for energy-intensive water extraction and electrolysis processes. For operations in permanently shadowed regions, power must be transmitted from remote solar farms via cables or beamed using microwave or laser technology. Alternatively, small nuclear fission reactors, like NASA's Kilopower project, could provide continuous power regardless of location or solar conditions. These systems would generate 10 to 40 kilowatts continuously, enough to power several small mining operations. Future fusion reactors using helium-3 could eventually replace these fission systems, offering greater power output with minimal radioactive waste. Communication delays between Earth and Moon, approximately 1.3 seconds each way, complicate remote operations. This latency necessitates semi-autonomous systems capable of making operational decisions without continuous human input. Artificial intelligence and machine learning algorithms will enable equipment to adapt to changing conditions and identify resource-rich areas independently. The reduced gravity environment affects fluid mechanics, material handling, and structural design. Processes that rely on gravity separation on Earth require complete redesign. However, the lower gravity also offers advantages, allowing larger, more fragile structures than would be possible on Earth. Transportation infrastructure represents another engineering hurdle. Moving extracted ice from shadowed craters to processing facilities requires specialized vehicles. Traditional wheels struggle in loose regolith, leading engineers to develop alternative mobility systems like screws, tracks, or even jumping mechanisms that minimize contact with the abrasive surface. Companies like Astrobotic and Marston Space Systems are developing robotic landers capable of delivering mining equipment to precise lunar locations. Their designs incorporate shock absorption systems to protect sensitive equipment during landing and dust mitigation technologies to prevent engine damage during takeoff and landing operations. Despite these challenges, the engineering community has made significant progress. NASA's Break the Ice Lunar Challenge has generated innovative concepts for excavation and transportation systems. The European Space Agency's Prospect instrument, planned for Russia's Luna 27 mission, will demonstrate ice extraction technologies. These initiatives represent important steps toward establishing the infrastructure needed for a functional lunar fuel station. The concept of lunar fuel production isn't merely a technical ambition. It represents a fundamental economic transformation in how humanity approaches space exploration. Currently, launching a single kilogram into low Earth orbit costs approximately $2,000. Sending that same kilogram to the Moon costs roughly $20,000. These prohibitive costs have constrained human space activities for decades. The economic equation changes dramatically when propellant doesn't need to be lifted from Earth's deep gravity well. Studies by the Colorado School of Mines suggest that propellant derived from lunar resources could eventually cost 80 to 85% less than propellant launched from Earth, creating a multi-billion-dollar lunar fuel economy. The initial investment requirements remain substantial. A comprehensive lunar fuel infrastructure, including prospecting equipment, mining machinery, processing facilities, and storage systems, could cost between $12 and $15 billion to establish. However, this investment becomes economically viable when amortized across multiple missions and customers. A detailed analysis conducted by United Launch Alliance, ULA, in 2022 projected that a mature lunar propellant operation could produce up to 200 metric tons of liquid oxygen and 35 metric tons of liquid hydrogen annually. At current launch costs, this represents roughly $750 million in value, delivered to lunar orbit yearly. Private capital has begun flowing into this potential market. Companies like Blue Origin, founded by Amazon's Jeff Bezos, have invested significantly in developing lunar landers capable of delivering mining equipment to the surface. Moon Express, Astrobotic, and iSpace are developing specialized vehicles for lunar resource prospecting. Meanwhile, established aerospace contractors like Lockheed Martin and Boeing are designing systems for propellant storage and transfer in orbit. The economic model follows a familiar pattern from Earth's industrial history: high initial investment, followed by declining marginal costs as infrastructure matures. Goldman Sachs estimates that the space economy could grow to $1 trillion by 2040, with lunar resources playing a critical role in this expansion. Government space. Agencies recognize that public-private partnerships offer the most sustainable approach. NASA's Commercial Lunar Payload Services, CLPS initiative, provides contracts to private companies for lunar transportation services, creating market demand that supports private investment. Similarly, Luxembourg has established a legal framework for space resource utilization and created a venture fund to support companies developing relevant technologies. The economic ripple effects extend beyond propellant production. Lunar water can support life support systems, radiation shielding, and agricultural needs for human outposts. Oxygen extracted from regolith could supply breathing air for habitats. Even the regolith itself has economic value as construction. Material for lunar structures, potentially manufactured using 3D printing techniques. A key economic factor is the development of standardized interfaces for propellant transfer. Just as shipping containers revolutionized global trade by creating standard interfaces between transportation modes, standard propellant transfer connections would allow any compatible spacecraft to refuel at lunar facilities. The Lunar Gateway will incorporate these standardized interfaces, creating an open architecture that encourages commercial participation. The business model could mirror Earth's resource industries, with separate entities handling extraction, processing, transportation, and storage, each specializing in their area of expertise. Alternatively, vertically integrated companies might control the entire supply chain, similar to early oil companies. Insurance and liability frameworks represent another economic challenge. Traditional space insurance policies weren't designed for resource extraction activities or in-space refueling operations. New financial instruments and regulatory frameworks will need development to manage these risks appropriately. Currency and payment systems present interesting questions. Would transactions occur in Earth currencies, or would specialized space-based currencies emerge? How would resource rights be defined and traded? The 2015 Luxembourg Space Resources Act and the U.S. Commercial Space Launch Competitiveness Act began addressing these questions, but many details remain unresolved. Despite these unknowns, economic forecasts remain optimistic. A 2024 report from the Artemis Project Office estimated that lunar propellant production could reduce the cost of Mars missions by 30 to 40%, potentially saving taxpayers billions while accelerating exploration timelines. For commercial satellite operators, lunar-derived propellant could extend satellite lifespans by enabling affordable refueling operations, creating additional economic value. The lunar surface has become the focal point of a new space race, one centered on resource utilization rather than ideological supremacy. Unlike the Cold War competition that drove the original Apollo program, today's lunar ambitions reflect a complex interplay of cooperation and competition among nations and private entities with diverse motivations. The United States leads the Artemis program, which has expanded beyond NASA to include international partners. The Artemis Accords, signed by 24 nations as of early 2025, establish principles for cooperation in lunar exploration and resource utilization. Signatories include traditional space powers like Canada, Japan, and the European Space Agency members, alongside emerging space nations like Brazil, Saudi Arabia, and the United Arab Emirates. These accords explicitly recognize the right to extract and utilize space resources, a position that builds upon the 1967 Outer Space Treaty, while addressing modern commercial interests. By creating a framework for responsible resource utilization, the accords aim to prevent conflicts over lunar territory while enabling economic development. China pursues its own ambitious lunar program independent of Artemis. The Chang'e missions have systematically built Chinese capabilities, from orbiting the Moon, Chang'e 1 and 2, to landing and roving, Chang'e 3 and 4, to sample return, Chang'e 5. The Chang'e 6 mission, planned for 2026, targets the lunar South Pole, the same region of interest for water ice mining. China has announced plans for an International Lunar Research Station, ILRS, in partnership with Russia, with construction projected to begin in 2030. This parallel program creates competition, but also opportunities for scientific exchange. While political tensions limit direct cooperation between the United States and China in space, third-party partners create indirect bridges between the programs. Russia's lunar ambitions have evolved through political and economic fluctuations. After the Lunar 25 mission failure in 2023, Russia has realigned its lunar strategy toward the joint project with China, while maintaining limited involvement with Western partners through the European Space Agency. India has emerged as a significant lunar player with its Chandrayaan program. The successful Chandrayaan-3 landing near the lunar South Pole in 2023 demonstrated India's growing capabilities. The Indian Space Research Organization, ISRO, has announced plans for a sample return mission by 2028, potentially providing valuable data on resource distribution. Japan's JAXA space agency has specialized in precise landing technologies, demonstrated by the SLIM mission's pinpoint touchdown in 2024. This capability is crucial for accessing specific resource-rich areas. Japanese lunar plans emphasize innovative technologies like the transformable lunar robot, developed with Toyota, designed specifically for resource exploration. Private companies add another dimension to this international landscape. US-based firms like Astrobotic and Intuitive Machines have secured NASA contracts, but are also developing independent commercial capabilities. Japanese company iSpace, despite its first mission failure, secured significant investment for future lunar resource ventures. Luxembourg-based companies benefit from that nation's progressive space resource legal framework. Scientific collaboration continues alongside this competitive environment. The International Space Exploration Coordination Group, ICCG, comprising 26 space agencies, coordinates planning to minimize duplication and maximize scientific returns. Data sharing agreements ensure that resource mapping information contributes to a common scientific understanding, even as nations and companies position themselves for potential commercial advantages. Water ice at the lunar poles represents both the greatest opportunity for collaboration and the greatest potential for conflict. The permanently shadowed craters contain finite accessible resources, raising questions about fair access and utilization rights. The principle of non-interference established in space law provides a foundation, but practical implementation remains undefined. Some experts advocate for an approach similar to Antarctica's scientific reserves, where certain areas would be protected from commercial exploitation to preserve them for scientific research. Others suggest resource development zones where controlled commercial activities could proceed under international oversight. Standardization presents another avenue for constructive engagement. Interface standards for propellant transfer, communication, protocols, and emergency response procedures would benefit all parties while enhancing safety. Organizations like the International Organization for Standardization, ISO, have established working groups focused on these specifications. Despite the competitive elements, lunar resource utilization may ultimately require collaboration simply due to the massive investment required. No single nation or company can realistically establish the complete infrastructure independently. The most likely outcome is a network of specialized facilities operated by different entities, but functioning as an interconnected system, much like Earth's global energy infrastructure. The establishment of lunar fuel production fundamentally reshapes the architecture of human space exploration, transforming mission profiles, spacecraft design, and our approach to deeper space missions. This paradigm shift could be as significant as the transition from coal to petroleum in the early 20th century, creating new possibilities while rendering old approaches obsolete. Traditional mission architectures follow what engineers call an all-up approach. Spacecraft depart, Earth with all the propellant needed for the entire mission. This necessitates enormous launch vehicles like NASA's Space Launch System, SLS, which stands 111 meters tall and costs approximately $2 billion per launch. In contrast, a lunar refueling architecture allows spacecraft to launch with minimal fuel, just enough to reach lunar orbit. After refueling with moon-derived propellant, the spacecraft continues its journey with full tanks. This approach, called lunar supplied, reduces the initial mass lifted from Earth by 60 to 70%. The mass reduction cascades through every aspect of mission design. Launch vehicles can be smaller and less expensive. Spacecraft can allocate more mass to scientific instruments, habitats, or radiation shielding instead of propellant tanks. Mission durations can extend as the limitation of carrying all necessary propellant is removed. For Mars missions, the architecture changes are particularly dramatic. NASA's current Mars architecture requires multiple SLS launches to assemble components in Earth orbit before departure. With lunar refueling, smaller commercial launch vehicles could deliver spacecraft components to lunar orbit, where they would assemble and fuel before continuing to Mars. A study by the Keck Institute for Space Studies concluded that using lunar-derived propellant could reduce the cost of Mars missions by $23 billion over a 20-year program, while increasing mission frequency and scientific returns. The same approach applies to missions targeting asteroids, Jupiter's moons, or other destinations. Vehicle design evolves to accommodate this new architecture. Spacecraft optimized for lunar refueling would feature larger propellant tanks relative to their dry mass, maximizing the benefit of available propellant. Specialized transfer vehicles might emerge, reusable space tugs that shuttle between Earth orbit, lunar fuel depots, and various destinations, never re-entering Earth's atmosphere. Propulsion technology selection also shifts. Chemical rockets, using liquid hydrogen and liquid oxygen, become more attractive since these propellants can be produced from lunar water. Alternative propulsion technologies like nuclear thermal propulsion, which offers higher efficiency than chemical rockets, might use hydrogen produced on the Moon as reaction mass. The orbital mechanics of mission planning evolve as well. Traditional trajectories minimize propellant use through gravity assists and orbital resonances, accepting longer travel times as the trade-off. With abundant propellant available, mission planners could select faster trajectories that consume more fuel, but reduce crew exposure to radiation and microgravity. For human missions, the architecture changes extend to life support systems. The same water harvesting techniques that produce rocket fuel can provide water for drinking, oxygen for breathing, and hydrogen for manufacturing methane when combined with carbon for various uses. This creates a more robust exploration system, less dependent on Earth for resupply. Space habitats would likely co-locate with fuel production facilities, creating transportation hubs similar to Earth's port cities. These settlements would expand beyond government operations to include private research facilities, commercial habitats, and eventually tourism infrastructure, all enabled by local resource utilization. Science missions benefit particularly from This architectural shift, planetary landers could carry additional scientific equipment instead of return propellant. Sample return missions become more feasible when the return journey can start with full propellant tanks. Telescope assemblies too massive for direct Earth launch could be constructed in space using multiple smaller launches and space tugs fueled with lunar propellant. The architecture extends to cislunar space, the region between Earth and Moon, which becomes more accessible with lunar refueling. This enables commercial applications like satellite servicing, space manufacturing, and large-scale space solar power systems that beam energy to Earth. These applications create additional demand for lunar propellant, strengthening the economic case. Even Earth orbit operations change with this architecture. Satellites reaching end of life due to propellant depletion could be serviced by refueling tugs that obtained their propellant from the Moon. This extends satellite lifespans, reduces space debris, and improves the economics of space-based services. On Earth, the lunar refueling architecture represents a transition from the current scarcity mentality in spacecraft design, where every gram is scrutinized, to a new paradigm where propellant becomes abundant and affordable. This shift enables designers to prioritize reliability, redundancy, and capability over mass minimization. The transformation of the Moon into a cosmic gas station will unfold over decades through a series of increasingly ambitious missions and technological milestones. While the full realization of a lunar fuel economy remains years away, each step builds upon previous achievements, creating a technological ladder reaching from Earth to the stars. The foundation was laid by orbital reconnaissance missions, like NASA's Lunar Reconnaissance Orbiter, and resource confirmation missions like L-CROSS, which first confirmed water ice in permanently shadowed regions. Current and near-term missions continue this preparatory work. Between 2025 and 2027, NASA's Artemis 3 mission will return humans to the lunar surface for the first time since Apollo, targeting the South Polar region. Astronauts will conduct initial assessments of surface conditions and collect samples from areas identified as potential resource deposits. Simultaneously, robotic missions like the Volatiles Investigating Polar Exploration Rover, VIPER, will map water ice distributions with unprecedented detail. By 2028, the first experimental ISRU demonstrations will begin operation. These suitcase-sized packages, delivered by commercial landers through NASA's CLPS program, will extract small quantities of water from regolith and demonstrate electrolysis in the lunar environment. While producing only kilograms of propellant, these technology demonstrations will validate critical processes. The Lunar Gateway, assembled in orbit between 2027 and 2030, will provide a platform for testing propellant, storage, transfer, and management in cislunar space. Initial experiments will use propellant launched from Earth, but will establish the protocols and technologies needed for lunar-derived fuel. The period from 2030 to 2033 will see the first semi-permanent human presence on the lunar surface with the establishment of the Artemis Base Camp. This facility will support rotating crews for missions lasting up to 2 months and will include the first pilot-scale resource utilization systems, capable of producing hundreds of kilograms of propellant annually. This modest production will support surface mobility systems and experimental rockets designed to reach lunar orbit with small payloads. The economic model during this phase remains primarily government-funded, with technology development as the primary goal rather than commercial viability. By 2035, assuming successful pilot operations, the first commercial-scale production facility could begin construction. Using largely automated systems, this facility would target annual production of 5 to 10 metric tons of propellant, enough to refuel small spacecraft or boost satellites to higher orbits. The latter half of the 2030s would see expansion to multiple production sites across the lunar poles, creating a distributed network with improved reliability. Private companies would likely take the lead during this phase, with government agencies becoming customers rather than operators. Annual production could reach 20 to 30 metric tons, making lunar propellant economically competitive for specific high-value missions. The The 2040s could witness the integration of lunar propellant into mainstream mission architecture. NASA's planned Mars missions would incorporate lunar refueling as a standard element. Commercial satellite operators would contract for in-space refueling services, and scientific missions throughout the solar system would base their designs on the availability of lunar propellant. By 2050, a mature lunar fuel economy could emerge, with annual production exceeding 100 metric tons. Multiple competing providers would offer specialized services, from raw propellant delivery to complete transportation packages. The cost per kilogram would fall to levels comparable to or below Earth-launched propellant when measured at the point of use in space. This timeline depends on consistent funding, policy support across multiple administrations, and success in overcoming technical challenges. Delays in any major component, the Artemis program gateway development or ISRU demonstrations, would push later milestones further into the future. Several critical technological thresholds must be crossed. Propellant storage systems must demonstrate multi-year retention of cryogenic liquids with minimal boil-off. Automated mining systems must achieve sufficient reliability to operate for years with minimal maintenance. Power systems, whether solar or nuclear, must provide consistent energy through the long lunar night. The economic threshold is equally important. For lunar propellant to become self-sustaining, production costs must fall below approximately $500,000 per kilogram delivered to lunar orbit, the point at which commercial customers beyond government agencies would find it economically viable. Yet despite these challenges, the direction of development remains clear. Each NASA budget, each successful CLPS mission, each new international agreement on lunar exploration brings us closer to the day when spacecraft will routinely refuel at the lunar gas station before venturing deeper into the solar system. The Sightings, moon once seen as a destination in itself, is being reimagined as the critical first step in humanity's expansion beyond Earth. Not merely a place to visit, but a resource to utilize, a foundation upon which to build our cosmic future. In transforming the moon into a fuel station, we transform ourselves from an earthbound species to a spacefaring civilization.